Hello future engineers, welcome to my YouTube channel. If you're new to my channel, please don't forget to subscribe because I promise to create a channel which will have complete contents of the subject matter that I discuss here. So it will be beneficial to you, to the students, to my subscribers, and to my future subscribers. So to keep me going, please share my videos to your friends, to your friends, so that's the only way you can also expose my channel to others. I hope that I can be of service to you. I can help you prepare in your chosen field, which is civil engineering. So I'll discuss here shear and moment equations. Shear and moment equations for beams, then the subsequent construction of the shear moment diagram, and hopefully the sketching of the elastic curve. So let's have objectives: to write shear and moment equations in beams to serve as equations in plotting the shear and moment diagrams. Apply static equations in order to draw the shear and moment diagrams as another tool. Then draw the shear and moment diagrams based on the defined or established equations for shear and moment. Then finally sketch the elastic curve or the deflected shape of the beam. Although not required, but it is a good practice to have the sketch of the elastic curve so that you'll be prepared for the deflection of the beam. So we define a beam as a flexural member, or a flexural member is frequently encountered in structures and machines, and its stress analysis constitutes the more important aspects of mechanics of materials. So this subject matter here. A beam is a member subjected to loads applied transverse to the long dimensions, causing the beam to bend, as shown in the figure. So remember the effect of forces or loads to deformable bodies. It will produce stresses and deflections, as shown. So if this is the neutral axis of the beam, the orange colored dust lines, then because of the effect of this loading, it will deflect as shown. Of course, this is highly exaggerated deflection. This will now be the neutral axis, and this is highly exaggerated for the purpose of visualization so that you can analyze deflections and rotations in the next chapter or topics. Of course, in reality, you cannot detect that the beam will bend this way due to the effect of the loadings, unless the loadings are excessive, but that's not allowed in structural engineering. Usually, you cannot detect this beam. This is highly exaggerated. You cannot detect that it deflects that way. It almost remains straight, and the exaggeration is for the purpose of visualization so that you can analyze. So a beam supported by pins, rulers, or smooth surfaces at the ends is called as a simple beam. So this is one example of a simple beam. It is supported by a pin and a smooth surface on the other end, or ruler. So that's a simple beam. There are two component reactions here, then one at B. So there are three component reactions, although the horizontal reaction at A is 0 for beams. Even if there is this horizontal reaction, it will cause axial it will be considered as an axial load, and in the preparation of shear moment diagrams, axial loads are not important. Only the shear and bending moment diagrams will be important here. So if either or both ends of a beam project beyond the supports, it is called a simple beam with overhang. So we have here the different beams. This is simply supported beam. We have a cantilever beam. We have an overhanging beam. Then this is a prop cantilever beam. So this is indeterminate to the first degree. We have fixed or restrained beam, indeterminate to the third degree. And we have here a continuous beam. So this is indeterminate to the second degree. So with time constraints, we will deal only with these first three types of beams, which are categorized as determinate beams. For these last three, although part of the mechanics of materials, they will be discussed in more details in structural theory. And if is of course, if we still have time, I will also discuss this for the benefit of those students and classes that discuss indeterminate beams. A cantilever beam is one in which one end is built into the wall or other support so that the built-in cannot move transversely, horizontally, vertically, or rotate. So this is a cantilever beam. The first three group of beams are statically determinate, as mentioned earlier, while the last three group of beams are statically indeterminate ones. So, of course, we will discuss this, but we will concentrate on the first three first. So, in the subsequent chapters, then these types of beams, the second group, will be discussed. So, the effect of the transverse load is to produce internal shear and bending moment, which in turn causes rotations and deflections of a section. These two internal forces, shear and moment, will be evaluated in this lesson, and the other effects will be discussed in the subsequent lessons. This one, for deflection purposes. We shall focus our attention to the determinate beams, and the indeterminate ones will be discussed in more details in the course structural theory. But we will also discuss it here because I will also discuss this here because of the subject matter itself. So loadings on the beam may either be a point load or concentrated load when a heavy equipment occupies a small area, and distributed load which vary with a great amount of area. So for example, this beam supports a floor, so the area is considerably large, so the load should be distributed like this one or this one, or if the load may vary with area such as a sand pile, or this may be the distribution of the load due to maybe pressure. But if it occupies a narrow area and the distribution is uniform, then it can be reduced to this, what we call line loads. We call this line loads, which varies with length. So this is an example of a concentrated load. These are concentrated loads or point loads. They are representative of heavy equipment acting over a small area. So even if the area is, let us say, 0.2 square meter or 0.3, as long as that area is considerably small compared to the area of the surface where they act or concentrated, then we can consider them as point load or concentrated load. So when the distributed load acts over a very narrow area, then it can be represented by a line load which is either uniform like the load on the cantilever beam or varies with length as in part C of the determinate beam. So which I already explained in the preceding slide. So this is line load that varies with length. The setting up of shear and moment equations is the same as finding the equations of functions. So shear function of x and moment also in terms of the distance x. Usually the left endpoint of the beam coincides with the beam is the origin, treated as the origin, and the axis of the beam, the neutral axis, coincides with the x-axis. So that's the preliminary idea, so that we can set up shear and moment equation. For shear, as a start, we draw the free body diagram. Then the equation is summation versus y, and there will be sign convention for shear, for the direction, and as well as for moment. So, for instance, this is the simple beam, this is the x-axis, and point A is the origin. So for these functions to be written correctly, sign conventions for shear and moment should be set up first. So for positive shear, when at the left section the shear is upward and the right section the shear is downward. So this is positive shear. At the left, up, and at the right, down. The effect of the shear force is to translate the section. So the effect, that's the effect. So this is the positive shear. So, or if the shear forces tend to rotate the segment of the beam clockwise. Then for positive moment, if the shape of the bending of the segment of the beam causes the beam to have this shape, smiley shape, then that's positive. It means that at the left section the moment is clockwise and at the right section is counterclockwise. Or if the top fiber of the beam is compressed and the bottom fiber of the beam is stretched. So this is in compression and this is in tension. Of course, the opposite one, the sad phase one, is the negative moment, wherein the moment at the left is counterclockwise and the moment at the right is clockwise for negative moment. So for positive moment, just remember if the portion of the beam, segment of the beam causes this smiley face shape, then it is a positive moment, or clockwise at the left, counterclockwise at the right. The procedure for writing the shear and moment equations of a statically determinate beam, as well as the plotting of the corresponding shear and moment diagrams, are summarized below and should serve as your guides. So first, compute the support reactions from the free body diagram of the entire beam. So if this is the beam, which will be our first example later, so we need to compute for the reactions. Summation moment B0. So AY times 4.8, then minus 90 times 2.4, 1.2 plus 2.4, 3.6, minus 150 times 1.6 minus 150 times 0.8 equals 0. So you'll get AY equals 237. I will show that in details in the first example. And summation moment about A, the same manner, you can solve RB equals 279 kilonewtons. So divide the beam into segments so that the loading within each segment is continuous. Thus, the endpoints of the segments are discontinuities of loadings, including concentrated loads and couples. In the above segments, the segments that must be considered and divided would be segments AC, CD, DE, and EB. So there will be 4 segments because there are 4 segments with variations in loadings. For each segment of the beam, perform the following. So introduce an imaginary section, for example in AC, imaginary cutting plane within the segment located at the distance x from the left end of the beam, from the origin normally, that cuts the beam into 2 parts. So one from the origin to that section and the other one from that section to the right. So of course we select the one that is simpler, and that is from left to the first section. So this is the section and its distance from the left is x. Then we call this the shear here as shear in AC, and the moment which is down because this is the right section. Remember sign convention for positive shear, and moment is counterclockwise. Then we analyze this segment of the section. After analyzing this and writing the shear and moment equations, then we proceed to the next section CD, and so on and so forth. So that is X. Draw a free body diagram for the part of the beam lying either to the left or to the right of the cutting plane, whichever is more convenient to you. At the cut section, show the shear and moment acting in their positive directions so that we can write shear and moment equations. In particular, if the section is CD, for example, you just put subscript CD here, and for moment CD. So meaning to say this shear and moment equations will be plotted later for values of x within segment CD. So it's not applicable for any other segments, only for segment CD. And we must define the range of values of x for that portion, for segment D also, and so on and so forth. It's like defining functions for shear and moment. So for instance, this is shear AC and moment AC. Remember the positive sign conventions for shear and moment. For the right section, A is the left, this section is the right section, so downward for shear, positive shear, and counterclockwise for positive moment. Determine the expressions for shear and moment from the equilibrium equations obtainable from the free body diagram. So later on, as you accustom in drawing or imagining the free body diagram of the section, then there will be shortcuts anymore for setting up the shear and moment equation. So it needs shortcut. So shear in AC is equal to, for example here, summation versus y equals 0 for the segment. So 237 minus 90 times x minus shear AC equals 0. So therefore, shear AC is 237 minus 90 times x. The shortcut therefore is shear in AC is simply upward minus downward force. So that's it. That's the shortcut. For moment also, so you sum up moment about this section here. So this will be the equation, 237 times x, then because that's clockwise, then minus counterclockwise moment, 90 times x over 2, then minus MAC equals 0. So therefore, the shortcut to MAC is clockwise minus counterclockwise. So 237 times x minus 90 times x over 2, so minus 45x squared. So MAC is 237x minus 45x squared. So these are the equations for this segment, and you do that for each segment. And anyway, we will have this in our first example in this slide. So plot the expressions for shear and moment for the segment. It is visually desirable to draw the shear diagram below the free body diagram of the entire beam, which I do in this example. Of course, we will do that even in the books. That's the proper way so that later we can show the relations among the load on the beam, the shear, and the moment, bending moment. So, and then draw the moment diagram below the shear diagram. The bending moment and shear force diagrams of the beam are composites of shear and moment diagrams of the segments. These diagrams are usually discontinuous and or have discontinuous slopes at the endpoints of the segments due to discontinuities in loadings. So they may be continuous or discontinuous depending on the loadings, which you can predict when you are exposed to beams and loadings and you master the construction or drawing of the shear and moment diagrams. So that's it. So here is our first example. For the beam loaded as shown, write the shear force and bending moment equations, then construct the shear force and bending moment diagrams, and sketch the elastic curve. Neglect the weight of the beam. So here is the given beam, which is the same beam in the preceding slides. And let's have the shear force diagram, or you may write capital V dash D. The unit will be in kilonewtons, and the bending moment diagram, or simply M dash D in kilonewton meter. So first, let's solve for the reactions. Let's call that AY and this one RB. So summation moment B equals 0, clockwise positive, so AY times 4.8 minus 90 times 2.4, and the moment arm is 1.2 plus 2.4, so 3.6, so minus 90 times 2.4 times 3.6 minus 150 times 1.6, then minus 150 times 0.8. Then we can now solve AY. AY is 237 kilonewtons as before. So we have 237. So likewise, we sum up moment about A. Do not use summation forces Y equals 0. Use that mentally using your calculator for checking these reactions to make sure that the reactions are correct. So MA is summation moment A is 0, counterclockwise positive, so RB times 4.8, then minus 90 times 2.4 times 1.2, then minus 150, 0.8 plus 2.4 is 3.2, so minus 150 times 3.2, then minus 150 times 3.2 plus 0.8, so 4, minus 150 times 4. Then R sub B is equal to 279 kilonewtons. Then you have to check 237 minus 279, do not show here. Then minus 90 times 2.4 minus 150 minus 150. If it is 0, then that guarantees that all these reactions are correct. So next, let's have section AC first. We cut a section. Then the distance from A, which is the leftmost point, is X. Then because this is the first example, I'll draw free body diagram in more details for this portion as well as for CD. Then for the next section, we have to analyze because we ran out of space. So this is the free body diagram from A to this section here. So that's the distance X, this is AY, and let's put the positive direction of shear in AC, and moment in AC. So downward and counterclockwise for the right section. So supposedly, as a beginner, if it is new to you, the equation for shear is you just sum up forces vertical. So summation forces vertical equals 0, upward positive of course, so 237 minus the equivalent area of this loading from statics is 90 times x, that one, downward, then minus shear in AC, downward, equals 0. So this is equivalent to summation versus y equals 0. Therefore, shear AC is 237 minus 90x. So that's the shear equation for segment AC. Now, what's the shortcut? The shortcut is, if this is the right section, the shortcut is just upward minus downward force. So shear in AC is upward minus downward force. So that's why shear in AC is upward, 237 minus downward force, which is equivalent to the area of this loading, 90 times x. That's the shortcut. Then for moment, summation moment about this section AC here equals 0. So clockwise positive. So 237x minus 90 times x, then moment arm x over 2, that one. Then, so clockwise positive, then minus counterclockwise, 90 times x over 2, counterclockwise, minus MAC, which is counterclockwise also, equals 0. So MAC is 237x minus 45x squared. So what is the shortcut for moment? For moment, if this is the left and that's the right, so it's just clockwise minus counterclockwise moment. So MAC is 237 times x, that's clockwise. Then minus 90 times x over 2, so minus 45x squared. And stop. Next, we consider free body diagram from A to section CD, as shown in the figure. So it's lengthy if we draw the free body diagram for each section. That's why for the next section, DE and EB, we just analyze considering the left and the right. Although we can consider the right section if it is simpler than the left section, and we will have that for portion DE only later on this slide. So we draw the free body diagram of this part, which is now shown here. So remember the shortcut for shear in CD and moment in CD. For shear in CD, upward minus downward. That's a shortcut, remember? So therefore, shear in CD is 237 minus 90 times 2.4 this time, because 90 times 2.4 is within this section here. So the entire distance 2.4 must be accounted for. So shear in CD is equal to 237 upward minus downward force, which is equivalent to the area of this loading, 90 times 2.4. It's no longer 90 times x because the loading is discontinuous in this portion here. So its length is only 2.4. So minus 90 times 2.4. Then we have to simplify that equation. So shear CD is 21 kilonewton. So that means it is constant. The graph is horizontal for that case. This is parabolic curve. Then for moment CD, the shortcut is clockwise moment about C minus counterclockwise. So moment CD is 237 times x, that's x, minus counterclockwise moment, which is the moment of this loading, 90 times 2.4, and the distance of its centroid from this section here is x minus 1.2. This is 1.2, half of 2.4. So the distance of the centroid from that section is x minus 1.2. So we subtract moment CD, therefore, is 237 times x minus 90 times 2.4 times moment arm x minus 1.2. So if we simplify this equation to 37 minus 90 times 2.4x, then negative 90 times 2.4 times negative 1.2, the simplified equation for moment CD is 21x plus 259.2. This function is aligned with positive slope, so it is inclined up to the right. This is a parabolic curve which is decreasing in value. And I will mention how to prepare the graph later. Then, after CD, we proceed to DE. So this time, we imagine that section. So the shortcut is preceding shear, then you just add or subtract the new loading within that section or segment of the beam. So this is X this time. That's a positive shear because this is the right section, then the positive moment in DE. So shear DE is equal to upward 237 minus 90 times 2.4. Then we have a new load here which is within this section here. So minus 150 because it is downward. So simplifying, shear DE is equal to negative 129 kilonewton. So it is also constant. Again, in setting up the shear equation for DE, the shortcut is preceding shear, which is CD 21, then plus minus the new loading in that segment because it is downward, so it is 21 minus 150. Preceding shear in CD 21. Then because we have a new load 150 downward, so minus 150. So the shortcut is 21 minus 150. So it will also give us negative 129. But if you're still confused, remember summation forces y is the equation. And you just consider the free body diagram from A to that section. And remember this positive sign convention for shear and moment. Then for moment, the shortcut is supposedly preceding, then the moment of the new load, which is minus 150 times this moment arm. This distance is x minus that distance there, 3.2. So moment DE is 237 times x if we start from the beginning, minus 90 times 2.4 times quantity x minus 1.2. Then we have a new loading which is minus 150 times x minus quantity x minus 3.2. Or the shortcut is because this simplifies to that preceding value 21x plus 259.2, then we will just include negative 150x, then negative 150 times negative 3.2, which is negative 150x, then negative 150 times negative 3.2 is 480. So preceding moment in the preceding section plus minus the moment of the new load within that segment, within that free body diagram in that segment. So MDE is negative 129x plus 739.2, which is a line, straight line with negative slope, so it is going downward. That's the function. Then finally, for portion EB. So, but before that, let's have instead of considering the segment DE, considering left and up to that section, this time we consider that section to the right because it is simpler. So this now, section CE will be the left section if we consider the right portion of the cutting section. Remember, the cutting section will divide the beam, entire beam, into two parts. And for the preceding section, we always consider the left part. This time, I'll present a situation where we consider the right portion of the cutting section because it is simpler. So the positive sign convention, shear DE is upward and moment DE is downward, is clockwise this time. And for shear, the positive shear DE therefore is downward minus upward. Because if we consider the left portion, it was upward minus downward. So that's the shortcut. If you're still confused, then you just set up the equation summation versus y equals 0. It will give us the same result. So therefore, this is 4.8 minus x because the distance from A to that section is x. The length of the beam is 4.8. So this distance is 4.8 minus x. So if this is x also, the distance of this 150 kilonewton load from this section, because its distance from the left is 4. So this is 4 minus x. Not shown here, but remember this is 4 minus x, distance of 150 from that section. So, or shear DE, this is considering the right section, is equal to downward force 150 minus 279. So it will give us the same answer of negative 129. Same as when we consider the left portion of the cutting section. So if you're confused with this, just sum up forces vertical. Shear DE minus 150 minus 279 equals 0. So shear DE is equal to 100 shear DE minus 150 plus 279 equals 0. So therefore, shear DE is 150 minus 279. That's why you'll get negative 129. The shortcut is opposite to the sign convention when we consider the left part. So the shortcut is for shear downward minus upward. That's it. Then for moment DE, counterclockwise, the shortcut is counterclockwise moment positive. 279 times 4.8 minus x quantity, then minus 150 times quantity 4 minus x. That's the shortcut. If you're confused, then you just sum up moment about section DE, then equate to 0. Then you can set up the same answer. So moment DE is counterclockwise moment, 279 times quantity 4.8 minus x, then minus 150 times, remember I mentioned that this is 4 minus x. Then simplify. Simplifying, 279 times negative x, then plus negative 150x. Negative 150 times negative x is 150x. So you'll get negative 129x. Then the constant 279 times 4.8 minus 150 times 4 is 739.2, which is the same as that when we considered the left portion of the cutting section on the beam. So it will always give you the same answer. Now the advantage of considering the right section this time is it is simpler than the left section. But actually, if you are good in shear moment equation, that's also simple, either the left or the right. Then finally, let's have, because I only present the right section for section DE, for section EB, let's consider the left section to continue. So that's the section, and the distance from the left is x again. And that's the positive shear. Positive moment is counterclockwise this time. And the shortcut was, we have a new load which is downward, shear DE. So preceding shear, which is negative 129, then minus 150. So shear EB is preceding shear negative 129. We have a new load of 150 downward, so minus 150. I want you to show that it is also negative 279 by considering the right section, but remember the positive shear is upward and the positive moment is clockwise for EB. Then show that it is negative 279 considering this section here in your free time. Then moment EB is preceding moment in DE, negative 129x plus 739.2. Then we have minus 150 times this distance is x minus 4, because that's 4 meters, so this distance is x minus 4. So the additional moment is preceding, and minus 150 times quantity x minus 4, simplifying, MEB is equal to negative 279x plus 1339.2. So you just combine like terms, then that's the result. We are now ready to plot the shear force and moment diagram. So for shear AC, 237, so set x equals 0. The range of values for x would be 0 to 2.4 for segment AC. So when x is 0, it is 237 as shown. So when x is 0, then when x is 2.4, that is also defined in portion AB. So 237 minus 90 times 2.4. Remember, this is a straight line which is sloping downward. So connect 237 and the value when x is 2.4. 237 minus 90 times 2.4 is 21 when x is 4, right? Then it should be connected with a straight line because that's a straight line with negative slope sloping downward. So you should know that because that's a problem in algebra or in analytic geometry. You might not be able to interpret that that's a line. So you review analytic geometry, or else you are lost in this subject. You're not supposed to be in the mechanics of materials course because your problem is mathematics. Next is shear CD, which is 21. So it is continuous, 21, straight line, horizontal, because it is constant. When x is 2.4, 21. When x is 3.2, shear in CD is also 21. So that's how you have a constant value 21 there. Then next is, after CD is DE. Shear in DE is negative 129 when x is 3.2, negative 129. So from 21 down to abruptly change to negative 129. Then when x is 4 at E, it is still negative 129. So horizontal, constant. So that's negative 129 also. Then for section EB, it is negative 279. When x is 4, negative 279. So it abruptly dropped to negative 279. And when x is 4.8, it is still negative 279. So that's why we have horizontal free body diagram. So it must close because the reaction here is 279. So that checks. That's the shear diagram. In other books, in other manuscript, they are shading this diagram under the shear diagram for that's only for attraction, but you may not if you want. So I will not shade that. It will be a waste of time if I'm going to shade that. That's enough. Next, for moment AC, when x is 0, moment AC rather. When x is 0, moment is 0. So it begins with 0 value. Then when x is 2.4 for segment AC, 237 times 2.4 minus 45 times 2.4 square. The value is 309.6. Use your calculator. 237 times 2.4 minus 4.5 times 2.4 square. So 309.6. But the problem is, how do I know that the curve is like that? Why not like this? Remember, this is a parabola second degree curve, so it must curve. It is not a straight line in the first place. So since it is your first time, it is sloping up to the right and it is decreasing. You just describe the shear diagram, shear force diagram. So actually, later on, the 237 is the slope of the initial tangent here, and the slope decreases to positive 21. So the tangent here is 21. You describe the variation in the ordinates in the shear diagram. So it is positive and decreasing. So the slope should be positive. That's positive slope, and it is decreasing. The other way is you compute the value of this moment when x is half of 2.4, 1.2 for example, and show that when x is 1.2, it is greater than half of 309.6, so that it is above half of 309.6, so that you will have an idea, as long as it is curved, that it is above. So you evaluate 237 times 1.2 minus 4.5 times 1.2 square, and that will be less than half of 309.6. So you just estimate an intermediate value so that you can sketch the graph correctly. So that's my way for this situation here. Next is when x is 0 and when x is 2.4. That's already finished. Next is segment CD. This is the equation. It is a straight line with positive slope, so inclined upward. You substitute x is 2.4 first at C, then it will give us the same value of 309.6. You evaluate this, 21 times 2.4 plus 259.2. Then when x is 3.2, that's the boundary. So 21 times 3.2 plus 259.2, it will give us 326.4. And remember, this is the maximum moment where shear is 0. So remember the definition. Then we have set x is 2.4 and when x is 3.2. These are the values continuous. Then we proceed to dE, moment dE. This is the equation. So substitute x is, dE is defined for x from 3.2 to 4. So 3.2 first, negative 129 times 3.2 plus 739.2. It will give us the same answer of 326.4. Then when x is 4, negative 129 times 4 at E, x is 4, plus 739.2. So it should be sloping downward, and the value decreases to 223.2 when x is 4. Finally, for segment EB, substitute first x is 4, negative 279 times 4 plus 1339.2. It will give us 223.2, same. Then when x is at B, 4.8, negative 279 times 4.8 plus 1339.2, it will be 0, like that. So this is now the shear and the moment diagram. So that's completes this problem. And let's sketch the elastic curve because the moment is all positive. This is the moment diagram, positive. The positive bending is smiley, so the elastic curve will be also smiley, as shown in the figure. So that's the sketch of the elastic curve. So that's it for this problem. Example 4.2, derive expressions for shear and moment and draw the shear force and bending moment diagrams for the beam shown below. Neglect the weight of the beam. So this is the situation. We have a beam and loaded with line load, uniform load from the other right half. So for the procedure, we have to solve for reactions first, AY and R sub C. Summation moment C0. Then clockwise positive AY times L, then minus W times L over 2 times this distance of its centroid from the right is L over 4. So W times L over 2 times L over 4. Solving for AY is WL square over 8 divided by L, so WL over 8. So likewise, summation moment A0, counterclockwise positive RC times L minus W times L over 2. So this distance is L over 4 plus L over 2, so 3/4 of L minus W times L over 2 times 3/4 of L. So R sub C is 3/8 WL, and that checks because 1/8 of WL plus 3/8 of WL is 1/2 WL. So minus W times L over 2, so that's 0. If you sum up forces vertical, not shown here, you just check using your calculator or mentally. So next, let's have the values, and let's section AB here. So remember that we consider this segment, and the positive shear is going down, shear AB, moment is counterclockwise. So what's the shortcut for shear? Upward minus downward. Since there's no downward force, so shear AB is just WL over 8. For moment, you just sum up moment about the section clockwise positive. So WL over 8 times X and nothing more. So MAB is WL over 8 times X. Next, for section BC, you may consider, in this case, left A, then right. Let's consider this left portion of the section, and you may also consider right portion of the section if you want, but remember the sign convention. So that's X. This is X minus L over 2, X minus L over 2, that distance. So this is the positive shear BC and positive moment BC. So the shortcut for shear BC is upward minus downward. The downward force is W times length quantity X minus L over 2. So shear BC is WL over 8 upward minus downward, W times quantity X minus L over 2. Simplifying, WL over 8 minus W times negative WL over 2, you can combine. So that is 5/8 WL, then minus WX if you simplify. So 5/8 WL minus WX. That's shear in BC. For moment in BC, clockwise minus counterclockwise moment. So clockwise is WL over 8 times X, then minus W times quantity X minus L over 2 times moment arm quantity X minus L over 2 over 2. So MBC is WL over 8 times X clockwise minus counterclockwise moment W times quantity X minus L over 2 times moment arm X minus L over 2 over 2. So simplifying, MBC is WL over 8X minus W over 2 times X minus L over 2 quantity square. So you may write MBC that way. So that completes the shear and moment equations. Now I will show that if we consider the right section, the result would be the same. So this is the left and this is the right section. So if we consider the right portion of the segment BC, this is the free body diagram, and sign convention for shear BC is upward positive and MBC clockwise positive. Remember that. For shear BC, remember the shortcut is downward minus upward. It is opposite if you consider the left segment, which is upward minus downward. So this time, downward minus upward. So or shear in BC is downward, W times quantity L minus X minus upward force 3WL over 8. Simplifying, WL minus 3/8 WL is same 5/8 WL over 8. Then minus WX. So minus WX is the same. For moment BC, remember, it is equal to counterclockwise moment minus clockwise moment. So opposite to the shortcut if we consider the left portion of the section. So BC is counterclockwise moment, 3WL over 8 times quantity L minus X. This is L minus X because this is, if that is X, then this is L minus X. Then minus W times L minus X, then distance L minus X over 2. So simplifying, MBC is 3WL over 8 times L minus X minus W over 2 quantity L minus X quantity square. You might suspect that because they are different looking, they are not equal. They are equal. Let me do the algebra. So MBC, let's expand this. WL over 8x minus W over 2 times quantity x square minus LX plus L square over 4. That's the expansion. So WL over 8x plus WLX over 2. So that's 5/8 WLX, then minus W over 2 times x squared minus W over 2x squared. Then the negative W over 2 times L squared over 4, that's negative WL squared over 8, if you simplify term by term. Now let's also simplify this to show that they are equal. So MBC is 3WL squared over 8 minus 3/8 WLX, then W over 2 times quantity L squared minus 2LX plus X squared. So let's combine like terms. Let's have this first. So we have negative 3/8 WLX and negative W over 2 times negative 2LX. That would be WLX. So WLX minus 3/8 WLX, that's 5/8 WLX, which is the same as this. Then we have negative W over 2 times X squared, which is negative W over 2X squared. And 3/8 WL squared minus 1/2 WL squared is negative WL squared over 8. So it's the same. So MBC is again negative W over 2L squared, then plus 3/8 WL squared, negative WL squared over 8, which is the same term as this. Then negative 3WLX over 8, negative times negative 2LX is positive WLX. So positive WLX minus 3/8 WLX is positive 5/8 WLX, which is this term here. Then negative W over 2 times X squared is negative W over 2X squared, which is this term here. So that's why they are equal, even if they look different in this figure. So we're now ready to plot the shear force diagram and the bending moment diagram. So for AB, it is constant at WL over 8 when X is 0 and when X is L over 2. So as shown in the figure, WL over 8, constant, horizontal. When X is L over 2, it is still WL over 8. Then for portion BC, there are only two segments. When BC is defined from L over 2 to L. So when X is L over 2, so 5/8 WL minus W times L over 2, that's still 1/8 of WL. That's why we have constant here. Then when X is L over 2, when X is L, 5/8 WL minus WL is negative 3/8 WL. And remember, this is a straight line with negative slope, negative W, so sloping downward. That's why when X is L, this is negative 3/8 WL. And the curve is straight because it is a first degree curve because of X to the 1. And the value here is negative 3/8 WL. How is this obtained? You set X L over 2 for BC. We have set already L over 2. The result is WL over 8. And set X at C L. When X is L, we have negative 3/8 WL. And remember, the reaction at C is also 3/8 WL. So it must close. So that's the shear force diagram. For bending moment MAB, set X 0, so it begins with 0, because when X is 0, this is 0. By the way, this distance when shear in BC, because this is portion BC, is 0, so you just set this to 0. So equate shear BC to 0, cancel W, so X is 5/8 L. So this distance is 5/8 of L. So again, for moment AB, X is 0, so it's 0. When X is L over 2, because AB is defined from X0 to L over 2, WL over 8 times L over 2 is WL square over 16. And it is a straight line, first degree. So the value is WL square over 16. Then here, in portion BC, moment BC, you set X in this equation L over 2 first. So when X is L over 2, this is 0. It will give us WL over 8 times L over 2, WL square over 16. Next, when X is, do not proceed to L yet. When X is 5/8 of L, when shear is 0, you'll get the maximum moment. So substitute 5/8 L in BC. 1/8 of WL times 5/8 L. Don't mind the WL square. 1/8 times 5/8, then minus 1/2 times 5/8 minus 1/2 square. It will give us 9WL square over 128. Again, you substitute 5/8 L here. You will get the ordinate here for moment. That's the maximum moment when shear is 0. When shear is 0, the slope of this line is WL over 8. Remember the definition. When shear is 0, the slope of the tangent here is 0, horizontal. That's why that's the maximum. Then this time substitute X is L, WL over 8 times L, WL square over 8 minus W over 2 times L minus L over 2. So that's L over 2 square. So WL over 8 times L, WL square over 8 minus W over 2 times L square over 4, WL square over 8 also, so 0. It is 0 and it's sloping down. It is a second degree curve and the curve looks like that. How do I know that the curve is like that? You just set an intermediate value and it is concave down. You describe the ordinate of the shear diagram. The shear is 0, then the shear here is negative, so negative slope which is increasing like that. Or you substitute an intermediate value, say L over, let's say 3/4 of L, then you plot. If you're still confused, then it is mostly scaled plotting so that you will have a correct moment curve. So you just plot intermediate value like 3/4 of L, then 7/8 of L. 2 points are enough, or even 1 point is enough. You evaluate this value here, and that's it. Since the moment is positive, then the elastic curve will all be concave up, smiley face, as shown in the figure. So that's it for this video. It's long, and we'll have more examples in the next presentation.